In the simulation that you did, you look specifically at ionic bonding. So in this note sheet, it has stuff about ionic bonding and covalent bonding. So we're going to focus on ionic bonding in this video. These first few slides are review of things that we have talked about before. These are very important to review, so I encourage you to pause and read over them. You will be responsible for the things on these slides, but I'm not going to go over them since they are review, and some of them were also covered in the simulation. Okay, so I'm going to fast forward to lattice energy. Okay, this is something new. So lattice energy is the energy required to break 1 mole of a solid ionic compound. So you saw in the simulation how an ionic compound comes together in what we call a lattice. You have one ion that's positive surrounded by negatives, and those negatives surrounded by positives, and it goes on and on. In order to break that apart is going to require a lot of energy. So lattice energy is the energy required to break 1 mole of a solid ionic compound. And when you break it apart, it's going to break into its gaseous ions. And remember, you're going to have cations and anions. This process requires, and I'm going to keep emphasizing that, you have to put in a lot of energy because the bonds are very strong. So we call that endothermic. You have to put in. And the value is positive. However, if you put a lattice together, so you take the positive and negative ions and you put them back together, that's going to give off energy. That is called exothermic. The energy is exiting, and that value will be negative. You'll see that on the next slide. When we take the lattice apart, so here's the solid, it's ionic, so it would be in a lattice. If we're going to break it into gaseous ions, that's going to take energy. So that would be positive. However, if we take those ions and put them back together, the exact reverse of what happened up here, then we will get that same energy back. So negative. Every single ionic compound has a specific lattice energy. Some of these numbers are really, really high, and some of them are a bit lower. It always takes a lot of energy to break apart a lattice, but some lattices are stronger than others. And so we want to look at why. What makes one ionic compound stronger than another ionic compound? There are 2 factors that affect the lattice energy, or the strength of the ionic compound. This comes from Coulomb's law. So if you'll remember, we did the Coulomb's law POGIL, where we talked about attractive force. There are 2 factors that affect the lattice energy, which is that attractive force between your ions. You see that right here. The 2 factors are the distance between the ionic centers, and that is based on the size of the atoms. And the other factor is the charge on the ions. And this is the absolute value of those charges. Okay, so it doesn't really matter if we're talking about positives or negatives. It's the absolute value. The main factor is the charge. So we're going to look at the charge first. If the charge is greater, then the lattice energy is also going to be greater, because you see the charges are on the top of this fraction. So if the charges go up, then the lattice energy is going to be stronger. The second factor, and we'll only look at this factor if our charges are the same. So if the charges are different, this is going to make the impact. But if our charges are the same, then we'll look at the distance between the ionic centers. If the size goes up, that's going to make these ions further apart if they're bigger. So if the size goes up, remember from Coulomb's law, distance is on the bottom here. So if the size goes up, the attractive force or the lattice energy is going to go down. So let's look at some examples of how this plays out. You are not going to do this calculation. Okay, you just need to understand how the equation works so we can tell if a number is going to be bigger or smaller. right? So what you'll be asked to do is to compare two compounds, like these two, and tell me which from each set has the highest melting temperature. I could also ask you which from each set has the highest or greatest lattice energy. So I could ask you which one has the highest melting temperature, the highest lattice energy, the highest bond strength, and why. So anytime we're talking about ionic bonds and how strong they are, that's going to determine how high their melting point is and how high their lattice energy is and how high their bond strength is. And remember, that is dependent on two things. We've got to look at the charges, and if the charges are the same, we're going to look at the size based on what we said on that last slide. So let's look at this one, LIF versus LII. Right? So first, LIF, charges. Li is +1 and F is -1. Li is +1 and I is -1. So we've got a 1, 1. Remember, it's just the absolute value. 1, 1 and 1, 1. Okay? Which one's greater? They're the same, right? So now we want to look at the size. Well, we know lithium is the same size as lithium. So we're thinking about these two compounds. We got two lithiums. And then we've got fluorine. I'll do that in the blue. So here's fluorine. And then we've got iodide. Okay, well, how does iodide size compare to fluorine size? Remember, when we go down, the atoms get larger. So iodine's going to be much bigger than fluorine. All right. Now remember, these are in a lattice, so you'd have a lot more fluorines and a lot more lithiums and a lot more iodines repeating. But which of these bonds would be stronger? Which of these would be harder to break? This one, because they can pack in tighter, right? This distance is much shorter, so this bond is much stronger, so this melting temperature is much higher. This has a longer bond, so less attractive force. All right, let's do the same thing on these two, magnesium chloride or magnesium oxide. Well, magnesium is +2 and chlorine is -1. Magnesium is +2 and oxygen is -2. So we've got a 2 and a 1 and a 2 and a 2. Which of those is going to have greater attraction for each other? A 2 and a 1 or a 2 and a 2? Greater absolute value for the charges means a stronger bond and a higher melting temperature. So this one is going to have a greater lattice energy. All right, same thing here, Na +1, F -1, Mg +2, I -1. +1 -1 or +2 -1. 2 and 1 is greater than 1 and 1. So this one would have a greater lattice energy. All right? So we're only going to look at the sizes like we did in number 1 if the charges are the same. If the charges are different, the charges make the difference. All right, on this slide, it summarizes what I just talked about in those 3 examples. And now I want you to do 1 through 7 on worksheet 4.1, and number 7 specifically has several examples like this. So on those, I want you to make sure you explain yourself on each of those answers.